So the last section that we're going to talk about involving limits is going to be limits at infinity. Now that sort of seems impossible. How can we find a limit at a place that really isn't a number? Infinity isn't a number; it's more of an idea or a place. Well, basically that means is you're finding the limit of a function as x continues to grow uncontrollably, either positively or negatively. And indeed, the idea is that some functions do have exact limits, because not every single function, as x gets bigger, 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 gets bigger themselves. There are functions out there that sort of stabilize a particular value. In other words, there are functions out there that have horizontal asymptotes. So that's sort of the rough layman's idea, is that limits at infinity, they're just horizontal asymptotes in disguise. And we did see horizontal asymptotes back when we studied rational functions. For example, the function f of x equals x squared minus 1 over x squared plus 1. If you were to graph that guy, pop into your graphing calculator or go into Desmos, you'll see that it does have a horizontal asymptote. Now, I'm not going to swap back and forth between Desmos and this screen here, so I'll just go ahead and do a rough, emphasis on rough, sketch, because my artistic abilities isn't the best. So if you were to graph this guy, he's going to look something like, I'm going to try to use tick marks to make it somewhat accurate. He's going to look something like this. Um, something that looks like that. I'm not perfect. I mean, it's a very ugly picture now that I'm looking at it. But as you go to the far, far, far right or far, far, far left, it tends to hug that line y equals 1. So we would say the limit as x approaches infinity of the function is 1. Now notice how it has a horizontal asymptote. It's hugging the horizontal asymptote both to the left and to the right. So we can also say the limit as x approaches negative infinity of f of x is 1 as well. So in general, that's what it means to find a limit at infinity. You're basically asking the question, where is the function trying to be? What is the function output trying to be when you look in the far, far, far right of the graph or far, far, far left of the graph? Now, we were able to answer this, we were able to look at it because we did have a graph in front of us. But just like what we discussed in 13.2, sometimes we don't want to graph. Sometimes we don't want to make a table of values. Is there an algebraic way of figuring this out? There is, but we sort of have to talk about a precursor idea first. So a little, background idea. Informally, we need to convince ourselves that if you take a small number divided by a big number, that tends to 0. And if you can't, if that doesn't make sense to you, or if you're not too sure, just whip out a calculator and do some test numbers, right? What's 5, which is relatively small, divided by 100? 12 divided by 10,000. You can go up to 100, right? 100 divided by, if it's really, really big, 100 divided by a billion. You're going to get a really, really small number. Now, I want to sort of add an addendum to that statement. When I say small, I don't really mean the magnitude, because technically, 1,000. People would say 100,000 is pretty big. But if you had 100,000 divided by 9999999999999999999, this 100,000 looks puny compared to this big giant number. So I want to sort of caution against using description like small and big. Think of it as the relative growth. Um, if the growth of the numerator is relatively small to the growth of the denominator, then it's always going to tend towards 0. So for instance, the limit as x approaches infinity of 5 over x, the numerator will always be 5, but the denominator is getting bigger and bigger and bigger and bigger and bigger. So that's going to be 0. The limit as x approaches infinity of, heck, I can even put that, no, I'll put 1,000,000 up here. But yes, 1,000,000 is a big number, but remember, x is tending towards infinity, so eventually x is going to be 1,000,000,000, 1,000,000,000,000, quadrillion, number that your brain can't even comprehend. This 1,000,000 is going to look puny compared to it, so it's eventually going to be 0. So long story short, if your denominator, if you have a fraction and the denominator is getting wickedly bigger than the numerator, it's always going to tend to 0 as x goes to infinity. We're going to exploit that idea to be able to find limits at infinity, because what we're going to do is we're going to sort of shrink or rewrite the problem relative to the biggest denominator. And that's sort of like the technique. The technique of finding limits at infinity. You want to divide every term by the largest power of the variable. What do I mean? Let's do the example that we did before. We know the answer should be 1, right? So the limit as x approaches infinity of x squared minus 1 over x squared plus 1. So what I first do is look at all my variable terms. So I only have 2 of them, this variable term and this variable term. And then what I do is I take the biggest exponent, the biggest degree. Well, in this case, they're both the same, 2. So what you're going to do is, mathematically, what you're doing is you're multiplying by 1 over the biggest exponent. But that has the net effect of dividing everything by the biggest degree. So what you're technically doing is multiplying everything by 1 over x squared. Again, we chose x squared because that was the biggest exponent we saw. But, like I said, limits x approaches infinity, that has the net effect of just dividing everything by x squared. All over x squared plus 1 x squared over x squared. Now, why do we care to do that? Let's go horizontal. X infinity. X squared over x squared is, of course, 1. 1 over x squared stays. X squared over x squared is, of course, 1. Plus 1 over x squared stays. Now we can apply the limit. Now, when we apply the limit, remember, limit is as x approaches infinity. This is a regular constant. This is a 1. It doesn't have any x's anymore. So this x approaches infinity does not affect that 1. X could be whatever it wants. That number 1 will stay as number 1 all day long because he's not controlled by x. Similarly, the 1 in the denominator isn't controlled by x, so they will stay themselves. But we have these terms here. Notice we have 1 over x squared. Well, we have 1 over 1 divided by a number that's blowing up to infinity. So essentially 1 divided by, this is wrong to say, but you can sort of think about it, 1 divided by, quote, infinity is going to be a really, really small number. These guys here will go to 0, and of course you're left with 1, as we expected. So that's the math, or that's the algebra behind why the horizontal asymptote of this function here is y equals 1. It verifies that it is the horizontal asymptote. So that's the general technique that you would use if you wanted to find limits at infinity. Just divide out the biggest exponent that you see. So let's just do, I don't know, another one here. Find the limit as x approaches infinity of 5x squared minus 6x plus 1 divided by x cubed minus 1. So the thing you want to do is divide out by the biggest exponent, either top and bottom, numerator, denominator, divide by the biggest degree of x's. And I hope everyone agrees that x cubed is the biggest amongst all of the terms here. So you're going to have 5x squared minus 6x plus 1. Each of those guys divided by x cubes all over x cubed minus 1. All of those guys divided by x cubed. So you're going to get the limit as x approaches infinity of, let's see here, 5 over x minus 6 over x squares plus 1 over x cubes all over, this guy right here is a 1 minus 1 over x cubed. So now when you apply the limit, anything that has a variable denominator will go to 0. This will go to 0, this will go to 0, this will go to 0, this will go to 0. So all you're left with is 0 over 1, which of course is 0. This guy has a horizontal asymptote of y equals 0. The limit as x approaches infinity is 0. So that's basically it. Limits at infinity. It's a very easy technique. Just divide out the numerator and denominator by the highest power of the entire problem. On the practice, you're going to see that they're going to give you sequences as well. It's the same concept, just divide them out. So limits at infinity, very easy to calculate by hand. Pretty neat idea that when you go to infinity, sometimes functions stabilize. Who would have thought?